Welcome, AP Stat students, to another exciting day of statistics. Today's lesson is really all about vocabulary and learning some concepts. There's no calculations involved. So I'd like you to start by watching the video on the idea of the placebo and the placebo effect that I posted, if you haven't already watched it, because today's topic is how do we design experiments? And when we experiment on humans, the idea of the placebo effect is quite important to the design of human trials, human experiments. So make sure you understand what that word means and why we have to pay attention to the placebo effect when we experiment on humans. Okay, so we're basically going to spend a lot of time going over vocabulary and concepts, and then at the end we'll do kind of a sample problem. Okay, so the first thing you have to understand is what is an experiment? Okay, we have observational studies and we have experiments. Now, an observational study, I believe I might have mentioned this in one of the previous lessons. It's why scientists for years and years and years talked about, well, we can't say with certainty that smoking causes cancer because all we have is observational data, right? That data said people who smoke tend to have higher rates of lung cancer, but we couldn't say for sure that it was the smoking, right? It could have been some other cause. And that's why it's called a study, because the study, we're just gathering data. We're not trying to influence responses in any way. Whereas with an experiment, we're actually imposing a treatment on our subjects, and we're trying to control for lurking variables. We're trying to control other possible factors. Okay, so we've never been able to do a true experiment on humans and smoking because it would be unethical. And there's plenty of other things that would be unethical to do on humans. And of course, we can also talk about unethical experiments on animals as well. So when we can't do an experiment because of ethical reasons, that's when all we can do is observe. And so that's an observational study. We're not having any actual input on the subjects. We're simply gathering data that is, oftentimes after the fact. We look at medical records and things like that. Okay, when we set up an experiment, we will be imposing at least one treatment on our subjects or experimental units. We call them subjects, obviously, if they're humans, experimental units if potentially it's something else. And our treatments, we're typically going to have different levels, right? Different, if it's a drug, maybe different dosages, maybe given at different times, etc. So that's our explanatory variable. And those different levels we call the factors. Okay, now, when we are designing the experiment, we have to decide how our subjects will be assigned to the different treatment groups. And the key thing is when we are assigning our subjects, we need to use randomization, right? We'll talk more about that in a minute, but here's the three basic principles of designing an experiment. We need to control for lurking variables. Oftentimes that's done by having what we call a control group, or sometimes a placebo group. The placebo group would be a group that gets a fake drug, right? Something that should have no effect. Versus we can also have a control group, as our video mentioned earlier. It can simply be comparing the old treatment with a new treatment. Okay, so in which case the old treatment would be the control group. Okay, so we need a control. We need randomization because we want to make sure that our subject groups are as similar as possible. We don't want to have any bias when we assign our subjects to the different treatment groups. And lastly, we need replication. Okay, we need to be able to repeat, and see that, yeah, we're getting the same results over and over and over again. If we just do something once, we really don't know if that was the typical outcome or not, right? The more times we do something, we can see the distribution and we can see the probability of all the different possible results, okay? And we get that through replication. Okay, so we're gonna go into a little bit more detail now. The control group. Again, this is hugely important. We need the control group so we can compare, right? Imagine if I have some treatment that I claim makes all the students in my classes smarter. Well, what if I gave that treatment to every single student? I wouldn't know if it worked or not because I'd have nothing to compare to, right? So that's why we need a control group. We need to be able to compare. If I give it to every student and then all of my students say, oh yeah, I feel smarter, well, is that the placebo effect or is that the actual treatment? So again, we need a control group. We need something to compare to. Okay, next is the idea of randomization. Okay, so again, we need to randomly assign subjects to avoid bias. How do we carry out randomization? Well, typically we use random digits. So a random integer feature. We have one of those on our calculator, by the way. Let me show you where that's located. So if we go to the math menu and we go to probability, number 5 is the random integer command. So I can choose that. The way it works is you give the lowest integer that you're willing to accept. Oftentimes it's 1 because I start numbering my subjects with the number 1, but sometimes I start with the number 0. So let's say I have 30 kids in a class and I want to randomly select one student. I could say 1, 30 in my random integer. So it's going to give me a number between 1 and 30 inclusive. And then I would hit enter and it'll give me one such number and I'd go, oh, congratulations, student number 29, you've been chosen. Now, let's say I want to select 5 students out of my class of 30. What I would do is add one more comma. So lowest acceptable number, integer, highest acceptable integer, and then how many integers do we need from that? And then when I hit enter, there we go. It spits out 5 students that have been selected randomly. So that's how we do it on our calculators. It's quite fast, quite handy. The other way to do it, of course, is with a random digit table. I've provided you with such a table. It's labeled table B in your, I believe I provided it to you. I don't know. Hopefully I did. But anyway, table B, it's in your book. If it's not in the handout document that I put on Canvas, it's in your book. So what'll happen is typically I'll tell you on a test to use this because now I know what numbers you're looking at and I can grade you. Whereas with the calculator, we're all going to get different numbers unless we all have the calculator like fresh out of the box, then it starts at the same spot on its table. There is a way we can tell our calculators to all. It's called seeding your calculator to tell your calculator to go to a certain spot in its random digit table. That way we all will get the same answer and we can grade ourselves. But anyway, I'm not going to do that. I'll just use your digit table on the test. So make sure to bring this to the test. And I'll say something like, use line 114, and then you would have to assign the numbers. And what would happen would be you'd say, okay, first student selected is 45. Well, I don't have a 45, so you would just skip that. And then you'd say, okay, the next student selected is student 14. And I would have, obviously, I have 1 to 30, so I would have a student 14. Then I would have 93, then 29, so there's another student. 92, we skip, 75, 73, we skip, and then we get 06, and I go, okay, that's student number 6. Okay, so realize when you use the random digit table, that's how you get values that are between 1 and 9, is you get a 06 or a 05 or a 0 whatever. Okay, and realize once you go out to say over 100 students, like if I'm sampling a larger group, Now I have to give 3-digit numbers, right? And the way I would get a student who got, like student number 1 or something, I'd have to get 001, which I actually just saw that. So right here, I could get, 001. That would represent student number 1 if I had a larger, over 100 students. Okay. So anyway, that's how we use the random digit table. Okay, the final principle is replication, and I kind of already mentioned this. By repeating your experiment over and over and over again, we get to have a better feel for the different outcomes and how often we'll expect to observe those different outcomes. So in other words, it makes us more sensitive to the differences, right? We can be more confident in how the differences in drug dose or whatever it is that we're testing, we'll be more confident in what the results of those are. Okay. Lastly, we have to make sure, right? Sometimes we can set up an experiment that is so controlled and contrived that we get results that don't apply to the real world, right? Think about setting up an experiment in a vacuum, for example. Since there's no air, there's no anything out there, once you try to take it out of the vacuum and put it into the real world, maybe you get different results. Same thing, doing something in outer space where you have, different gravity or no gravity at all, right? So realize that statistics doesn't protect against these types of things. All right. We're going to go more in depth about comparison, or in other words, control. Sometimes when we're trying to compare, it makes sense to use what we call blocks. For example, maybe you think gender will play an important role in your experiment. So you don't really want to be comparing male versus female. So what you do is you would then block on gender, and we would say, okay, half of the males get, treatment A and half the males get treatment B, and then random assign. Then half the females get treatment A, half the females get treatment B, and again, random assignment. Okay, so that's called blocking. That way we are controlling for another potential variable. Right? In this case, that potential variable would have been gender. But it doesn't have to be gender. It could be age. It could be exercise, fitness level, something to do with diet. It could be your smokers and non-smokers, right? There's all kinds of different reasons that we might block. And again, the blocks that we form are potential lurking variables that we're trying to control for. Okay, another type of comparison is to use what we call matched pairs. Okay, matched pairs can be even more sensitive, of course, than blocking, because in a matched pair scenario, we can give one subject both treatments. Just give the treatments in a random order and make sure that there's enough time in between treatments, right? So the two treatments aren't confounding one another. So for example, you want to compare the effectiveness of, say, ibuprofen versus acetaminophen at relieving headache. So you would have, the person, the first time they get a headache, they get one of the treatments. The next time they get a headache, they take the other treatment. And then that same person can say, oh yeah, this one worked better on my headache. So anyway, that's called a matched pairs design, and you can have the same subject take both treatments in, again, random order. Other times, especially if it's a condition that would be unethical to leave it untreated, or it could be something where the condition is life-threatening and maybe the person deteriorates while taking the first treatment, and by the time they take the second treatment, you wouldn't have a fair comparison, that type of thing. So in these instances, we'll oftentimes do a matched pairs where we match up two subjects that have a similar, like a similar starting point. So maybe think of a disease, and you would find two subjects that are similar age, similar, demographic, and they have kind of the same level, stage 1, stage 2, or stage 3, right? The same level of infection of their disease. But it doesn't have to be disease. It can be anything. But again, we're just matching the two subjects up so that they're very similar, and then one subject gets treatment A and one subject gets treatment B, and then we can compare that way. Okay. All right, let's try a practice problem. So let's design an experiment. So let's say the Vaqueros Medical Association, the VMA for short, has developed two different energy bars. They're going to call one the V bar, the other the energy lasso bar. They want to test them on Irvine High students. So it's your job to set up this experiment and run it. They're going to provide you with a hyperness gauge so that you can read energy levels in our students. Okay? So here's the steps to designing your experiment. Okay. Step 1, you need to always name the population that you're interested in. Okay. Because that's the group that you're going to be able to generalize your conclusions to. So in this case, what's our population and what's our sample? Okay. Pretty simple. Hopefully you realize, all right, the population, we're testing it on Irvine High students, right? And then our sample would be the students that we choose to participate, right? Remember, that's the definition of a sample. If we gave it to every Irvine High student, that would no longer be a sample, right? Well, that would be the entire population, or in other words, a census. Now, you're expected to do this on every experimental design, whether the problem specifies what's the population or not. You should always mention, okay, our population for this experiment is, right, fill in the blank. All right, step 2. This is not something that you always have to do, but this is a commonly asked question. Okay, why would this be considered an experiment and not an observational study? Okay, well, answer is, we're going to be giving students these energy bars, right? We're not observing them. We are imposing the energy bars on the students, right? An observational study, we would simply sit back and wait for students to buy these energy bars and then get data on the students. But we're actually going to be imposing the treatment of giving the energy bars to the students. Okay. Now we're actually going to start getting into the design here. How could I choose 50 students, to be in my sample group? Okay. If we're using a simple random sample, we need to find a way to number the students and make sure every student has a unique number and that every student has an equal chance of being selected, and that every group of 50 has an equal chance of being selected. Okay, so I'll give you a second to think about how could you accomplish those goals. Right? The simplest way would, again, be give every student a number from 1 to 1,000, whatever, however many students we have, right? And then we pull out either our random digit table or our calculator and say, give me 50 numbers from the list. The nice thing about the calculator is I could specify, from 1 to 1,500 or something. Whereas when I use my random digit table, right, when I start looking at 4-digit numbers, I'm going to get a lot of numbers that are above 1,500 and therefore have to skip. So the random digit table can be kind of tedious when I have the majority of the numbers not representing any students or subjects. Whereas the calculator, I can make sure that every number it spits out represents a subject. Okay, but the calculator can, by the way, spit out the same number more than once, so you have to, again, disregard that when that happens. Okay. We could use ID numbers if we have a list of ID numbers, or we can number the students ourselves. So those are the kind of the two ways to set it up, and then random digit table or calculator. Again, on the test, I'm going to specify random digit table, and I'll tell you what row to use so I know what numbers you're looking at, and that way I can grade you. Okay, now when it comes time to actually get into the experiment itself, you have a couple options. You can diagram the experiment, or you can write like an algorithm, like step 1, step 2, step 3, or you could write it in paragraph form. Be comfortable with any of those methods, because you might be asked to any of those 3 techniques: diagram, algorithm, or write out a paragraph form. So let's start with the diagram. So when I make a diagram, what I do is I start with my population, right? So I have my population here, all Irvine High School students. Okay. Now, in this case, I have 2 different power bars. And by the way, this first setup that I'm going to make is going to be the most simple and really not the best choice. I just want to show you how to do a diagram, and then we'll talk about improving it. Okay. So since I have 50 students and I have 2 bars, I would randomly assign 25 to each bar, and then use my hyperness gauge and compare their energy readings. Okay, so this is just the simplest experiment you could run with comparison. Okay. Make sure, by the way, when you do your diagram, you must have random assignment somewhere in the diagram, and it must be in the appropriate place, right? We'll talk more about the appropriate places that design gets better. Okay. Take a second and think, do we have a problem with this experiment the way I'm running it right here? Yes, hopefully you see a problem, right? Our comparison groups both have been given an energy bar. So we don't know if both bars, it could be if the readings are the same, right, for both groups, it could be both bars are completely ineffective, and we have no idea of that, right? Could be both bars are extremely effective, but again, we have no idea of that if they're both just giving me the same readings. So we need to improve this a bit. We could use before and after readings on our hyperness gauge, but then we don't know if it's the placebo effect, right? It could be that it's just the placebo effect. Hey, here's an energy bar, eat it, and so people are feeling more energetic, even though it's just in their brain. All right, so let's make the experiment a little bit better. Step 1, let's say we think that freshmen, sophomores, juniors, we could throw seniors in there, but I didn't have room, so I left seniors off. But let's say we think grade level or age is an important variable that we want to control for. I don't know about you guys, but I've seen freshmen out there in the wild, and they are wild typically. So maybe if we have controlled for grade level in our design, we'll get better results. So this is called blocking, right? Remember that was the vocabulary word, blocking. Careful, it's very similar to a stratified random sample, but we don't say stratified because it's an experiment. When we talk about an experiment, we call it blocking. So very similar, kind of the same meaning in those 2 words, stratifying versus blocking, but make sure you use the right word in the right context, the right situation. This is called blocking. So again, we start with all students. Now the first thing we have to do is we have to do our blocks. So step 1, we are going to block by grade level because we were told that the grade level might have an important impact on our data. Then we can randomly assign from each block to our treatment groups. Okay. Notice I can't put randomization first. I see this on the test every year. Students will write randomly assign, and they'll say randomly assign who's a freshman, who's a sophomore, and who's a junior. Alarm bells should go off. Hey, wait a minute. Could I be in the freshman group? Only if you're a freshman, right? So that's the point of blocking. These are inherent characteristics of the subject. You can't randomly assign to a block. That can't happen, right? You randomly assign to a treatment group from a block. Okay, so blocking has to go first, then random assignment. Can't go the other way around. Okay, now the whole point of blocking is we would then compare within each group because we don't necessarily want to know the freshman versus the junior. We might want to know that, so we can compare again afterwards. But the key thing is we must compare within each block because we've now controlled for grade level, right, on this particular scenario because that's what we blocked on. We've controlled for it. Okay. Well, let's see if we can move on and make this better. Okay. So earlier I had already mentioned by only having two groups and they're both treatment groups, I don't know if I'm just observing the placebo effect or if I'm observing an actual change in energy level due to my energy bar. So let's improve our diagram by adding a placebo control group. Now, don't worry about what the placebo is, right? Oftentimes with pills, it's pretty easy to just give them, somebody a pill that is empty or something. But and they used to use sugar pills. Nowadays, you probably don't want to necessarily use a sugar pill because sugar, we know that can have an impact on people. And I know these are energy bars, and some of you might be thinking, well, how do I give a placebo energy bar, right? I might suggest a piece of cardboard because that's what they taste like, but don't worry about it. You just say placebo, right? And that's it. Leave it at that. Just say placebo energy bar. So let's rediagram. Step 1, all Irvine High School students. Step 2, we block by grade level. Step 3, random assignment, but now our groups are 3 treatment groups each, right? V-bar, lasso bar, and then placebo bar. And then we compare. And now we can see, did our energy bars both outperform the placebo, in which case they are truly energy bars, right? Did neither outperform the placebo, in which case they're really not energy bars, right? And then after comparing again within the grade level, that's the key, we can do a global comparison to see if grade level really did have an impact or not. Okay, so again, there's a diagram, and now I've basically improved the original diagram greatly. I've controlled for a lot more variables, much more sensitive. Okay, now here's something you may have heard of, double-blind experiments. Okay, first of all, whenever you have a placebo in your experiment, you must have a blind. Otherwise, it's pointless. If I walk up to subject A and say, here's your placebo, enjoy, hey, did that help? Right? Versus subject B, here's your actual treatment. Right? We've defeated the whole purpose of having a placebo group if we tell the person they're getting a placebo. So that would be called a single blind if the subjects are unaware if they got the placebo or the treatment. So a double blind is when the experimenters who are having direct contact with the subjects are also unaware if it's a placebo or a treatment that they're handing out. Okay, and you can hopefully see why that might be important. We wouldn't want the experimenters to subconsciously or even worse, purposefully impact the patient, right? Accidentally let something slip about the treatment. So it's safer to make it double blind. So how could I do that? Well, it's pretty simple. All you have to do is make sure that when in this case, the energy bars are handed out, there's nothing on the packaging that says, hey, placebo, right? The packaging of the placebo could just have a third name. that doesn't say placebo, but the person would think, oh yeah, this is an energy bar. Okay. Or you can not even put lasso bar, V bar, whatever bar on the packaging. You could just say A, B, and C, or you could just have 3 different colors, or 1, 2, 3, right? So that's how we accomplish the double blind. Then the experimenter would just say, okay, subject A got bar number 1, subject B got bar number 3, subject C got randomly assigned to this bar. And you just keep track of all of the results. And that way the subjects don't know what they got, placebo or energy bar. The people interacting don't know if it was a placebo or an energy bar. And you simply, keep track of that information. And then you send the results off-site, somebody who's not having any direct contact with our subjects. And then they know, oh yeah, bar number 1 was placebo, bar number 2 was a V bar, bar number 3 was a lasso bar, right? So that's kept off-site, away from everyone who's actually having any interaction with the subjects. Okay, so that's called a double blind. And the simple rule of thumb is a double blind is safer, right? It prevents any accidental or purposeful bias that could occur. So typically, anytime you're going to do a blind, it's good to do a double blind. But if the experiment says do a single blind, then in the single blind situation, there's a placebo. However, the experimenters, medical professionals in contact with the subjects would actually know, oh, this person's getting the placebo. And if you're a fan of medical dramas, there have been episodes I've seen where the experimenters find out, or they know, and then they're put in a moral dilemma, and oftentimes they end up compromising the experiment because of it. So anyway, that's the whole point of the double blind. Okay. Next, maybe instead of having our double blind blocked experiment blocked by grade level, maybe instead we could improve this experiment by doing a matched pairs design. So how could we run this as a matched pairs design? Okay, you can pause the video, think about it for a bit. Notice matched pairs design, we typically aren't going to say diagram it, because it's difficult to diagram matched pairs. Normally with matched pairs, we just use an algorithm or paragraph form. Okay, so one way to do a matched pairs, each subject will end up eating each bar, right? Each treatment. Just do it on a different day and compare the results that way. So we can see if one bar has a better effect than another bar on energy level. Okay, another option would be, instead of each subject trying each bar, we could match subjects by energy level who are in the same grade and compare the effects of the different bars that way, right? So those are the 2 different ways of doing the matched pair. And in this case, we could do either of the 2 methods, right? We could have each subject try each bar in a random order, or we could match subjects that have similar energy levels before the treatment. Okay. Now, do you see any weaknesses in this matched pairs design? Again, pause the video and think for a moment. Okay. One potential weakness I see is day of the week, right? If I have each subject serve as their own control and have a different bar on a different day of the week, different, classes are on different days. So it might be that, your student has a more difficult schedule on a certain day versus another day, or they had to stay up late for a test, studying for a test one night, etc. So there's a lot of lurking variables that can pop up because they're eating the different bars on different days of the week. Okay, so that's a potential lurking variable that is certainly a potential weakness to this experiment. Okay. And B, matching subjects by similar energy level. Well, there, remember, every person has their own, specific genetic makeup. And so having each subject eat both bars, we're now controlling for those different genetic factors. Whereas when we match subjects within the same grade level by energy level, now we're not controlling for that anymore. So they both have potential weaknesses. Okay, so there you go. That's lesson 5.2. And please, please, please read the book. Please focus on learning the vocabulary and practice with diagrams and practice with reading and writing things in algorithm form, etc. Because those are areas where students struggle. They struggle with putting the randomization in the right spot in their diagram versus where does the blocking go in their diagram versus writing things out in words. A lot of times students get a little bit sloppy. They're in a hurry, so they forget and leave steps out. So please practice and come to office hours and ask me questions if there's something that you don't understand. All right, thanks for watching.